I'm talking to you. This is Goddess of Science Physics, and I'm Mrs. Bolvin. And today we're going to talk about net forces and vectors. So a force, as you might realize, is either a push or a pull. Quite simply, just a push or a pull. When we use force in an equation, we're not going to write out force because that would take us too long. We're going to just use a capital F. And it's important that you use a capital F because a lowercase f actually means something different. It means the frequency of a vibration or a wave. So capital F it is. The unit for force in the metric system is a Newton, named after, yes, you guessed it, Sir Isaac Newton. And because it's named after a person, when we abbreviate it, we're going to use a capital N because he is a proper noun. So the net force is the sum of all the forces, either positive or negative, that are acting on an object. That's the net force. And here's kind of a crazy formula. So net force, and I use like the little subscript net to show that it's not like a force of gravity or a force of friction or something like that. It's a net force. So the net force is equal to the first force plus the second force plus the third force, etc. Now, just because you're adding them all together doesn't mean that all those forces are positive, and we'll get to that in a wee bit. So net force equals this little like weird E kind of thing is actually the Greek letter sigma, and that means the sum of all forces. So that's kind of a shorter way to write it, but this is actually this F net equals F1 plus F2 plus F3 for as many forces as you have is a little bit more practical. So, excuse me. Here's an example. Two people each pull on a llama with a force of 5 newtons to the right. What's the net force? Well, looking at our formula here, the net force is going to be the first force, which is 5 newtons, and then what the second person pulls, and that's 5 newtons. So the net force is going to be 10 newtons to the right. And it's really, really important that you put the direction on there, and we'll talk about that in just a minute. Because in physics, direction is really, really important. So here's another thing. That one was pretty easy, the 5 plus 5, because they're both pulling in the same direction, so they pull with twice as much force, which would be 10 newtons. So what if both people are pulling on a rope with equal force but in opposite directions? The rope won't move because the forces cancel each other out. Is that true? How does this work? And you know that from watching like the early stages of a tug of war. If they're both groups that are in the tug of war are pretty evenly matched, the rope isn't going to move hardly at all, if at all. So why is that? Well, let's explain it with some physics. So how does that work? So in science, there are 2 types of quantities. There are scalar quantities, which are just a magnitude, like length, 6 meters. That's just a magnitude. Time, 26 seconds. That's a scalar quantity. Mass, that's also a scalar quantity. But a vector has magnitude, but also direction, because direction is important for some of these quantities. Time never has a direction. Nobody ever says 23 minutes after 5 north. Okay, no one ever says that. So vectors are a different breed of cat here, and they have magnitude and direction. For example, force, 5 newtons to the right. If a vector quantity is negative, it means that it's just going in the opposite direction. It does not mean a number less than 0 as it does in math class. Negative numbers are numbers less than 0. Not true in physics, because remember, numbers in physics represent quantities. You can't owe velocity. You can't owe force. It means that it's in the opposite direction of something else. For example, -5 means 5 newtons in the direction opposite of whatever you called positive. So if positive was right, 5 newtons right, then negative would be 5 newtons left. So force net for 2 people pulling on a rope, both with the force of 5 newtons, but in opposite directions. So here's our little formula. And then we have 5 newtons. This is going to the right, and this is 5 newtons to the left. And because it's negative, they add to give you 0. So the net force on that rope, because they're pulling in opposite directions, is going to be no force at all, 0 newtons. So when you're writing vectors, a lot of times it's easier to help you to visualize it by using arrows to represent the vectors. The length of the arrow is going to be the magnitude, and the arrowhead is going to give you the direction that the arrow is going in. So if you have 2 newtons to the right, what are we going on? What's going on here? 2 newtons to the right, if they act in the same direction, add them. Okay, so there's 2 newtons to the right. Ignore the stuff that's down here just for a minute. And then you have 5 newtons to the left. So if they're acting in the same direction, if you had 2 newtons right and 5 newtons right, then you just add them together and it would be 7 newtons to the right. But because they're going in opposite direction, you have to subtract them. So 5 newtons minus 2 newtons is 3 newtons, but it's going to have the direction of left because that's the bigger of the 2 forces. The resultant is an arrow that represents a sum of 2 or more vectors, and sometimes if you're looking at physics problems, they'll ask you for a resultant. It's just the arrow that is the sum of 2 or more of these vector things. All right, well, thanks for joining me. Have a good day.